Let's go to electrostatics part 2. Relation between electric field and electric potential, which we had discussed last time. Let's revise. Work done by unit positive charge is equal to dW is equal to minus F dx, that is minus E dx when Q is equal to 1. Negative because the charge moves against force. Electric potential dV is equal to minus E dx, so therefore E is equal to minus d by dx of V. Thus, in an electric field intensity at a point is negative of the potential gradient at that point. Zero potential. 0 point is arbitrary but not insignificant. It is selected at convenience. In case of point charge or localized collection of charges, the 0 point is set at infinity. For electrical circuits, usually the earth is taken to be at zero potential. Thus, the potential at a point in an electric field is the amount of work done to bring a unit positive charge from infinity to that point. Electric potential due to a point charge, a dipole, and a system of charges. So let's take the electric potential due to a point charge. Let us consider a point charge at O plus Q. We bring it from the point M towards O. It reaches A at a distance R and M is at a distance X. So we have a displacement from M to N as dx. The electric field vector is away from O. Now we have the electrostatic force on a unit positive charge at M is of magnitude F is equal to 1 upon 4 pi epsilon naught into Q by X square. It is directed away from O along OM. For a small displacement dx from M to N, the amount of work done is negative because the displacement x and force are opposite, and that is dW is equal to minus F dx. The total work done in displacing the unit positive charge from infinity to point A, which is at a distance R, is given by W is equal to integral infinity to R minus F dx. And that comes out to be, we put the value of F as 1 upon 4 pi epsilon naught Q by X square. And ultimately, we get W is equal to Q upon 4 pi epsilon naught common, integral infinity to R x raised to minus 2 dx. And when we integrate, we get W is equal to minus 1 Q upon 4 pi epsilon into 1 upon R x square from infinity to R. So we substitute the values from infinity to R and you get the potential, that is nothing but the work done, is equal to minus Q upon 4 pi epsilon naught into minus 1 upon R plus 1 upon infinity. So the potential V is equal to W, which is equal to Q upon 4 pi epsilon naught 1 upon R. We have the positive charge particle produces a positive electric potential and a negative charge particle produces a negative electrical potential. So at R is equal to infinity, V is equal to Q upon infinity, which is equal to 0. Electrostatic potential at is equal to 0 at infinity. Thus we see V is directly proportional to 1 by R, and we already know E is directly proportional to 1 upon R square. So when you plot a graph of the potential or the electric field versus R, we get a graph like this, a curve like this for E and V, which is crossing each other. So we have the second one, electrostatic potential due to an electric dipole. So let us consider dipole plus Q minus Q at points A and B. Let us consider point C where we want to find the potential. So this distance is R1. So the potential at C due to Q at A is V1 is equal to plus Q upon 4 pi epsilon R1. Now similarly, this distance is R2. So the potential at C due to the charge minus Q at A is V2 is equal to minus Q upon 4 pi epsilon naught R2. So VC is equal to V1 plus V2. VC is equal to plus Q upon 4 pi epsilon naught R1 plus minus Q upon 4 pi epsilon naught R2. So VC is plus Q upon 4 pi epsilon naught 1 upon R1 minus 1 upon R2. Now let us consider this distance as R. We draw a perpendicular and this distance is L and L. And this becomes theta and it is 2 L sine theta. That is also here L sine theta. This is also L sine theta here. So the electric dipole moment is directed from the negative to the positive charge. R1 square is equal to R square plus L square minus 2RL cos theta. So R1 square is equal to R square into 1 plus L square by R square minus 2L cos theta by R. Similarly, we have R2 square is equal to R square into 1 plus L square by R square plus 2L cos theta by R. So we have for a short dipole, 2L is much less than R. If R is greater than L, 1 by R is small, L square by R square is neglected. Therefore, R1, we already have R into 1 plus L square by R square minus 12 R cos theta raised to half, and R2 is equal to R into 1 plus L square by R square plus 12 cos theta upon R raised to half. We neglect the term L square by R square and we get 1 by R1 equal to 1 upon R into 1 minus 12 cos theta upon R raised to minus half. And 1 upon R2 is equal to 1 upon R into 1 plus 2 by R L cos theta raised to minus half. So we already know VC is equal to plus Q upon 4 pi epsilon naught 1 upon R1 minus 1 upon R2. So substituting 2 and 3 in 1, we get VC is equal to plus Q upon 4 pi epsilon naught 1 upon R1 minus 2L cos theta upon R raised to minus half. Minus 1 upon R into 1 plus 2 by R, 12 by R 2S cos theta raised to minus half. Using binomial expansion, 1 upon xn is equal to 1 upon nx, x is much less than L, and keeping terms of the first order of L by R, then BC is equal to Q upon 4 pi epsilon 1 upon R into 1 plus L by R cos theta minus 1 minus L by R cos theta. Therefore, we get BC is equal to plus Q upon 4 pi epsilon 2L cos theta upon R square. Now we know Q into 2L is P, the electric dipole moment. So therefore, VC is equal to P upon 4 pi epsilon naught cos theta upon R square. Now we consider VC is equal to P cos theta upon 4 pi R square. We take the vector. We can use the dot product. So VC is equal to P vector dot R vector upon 4 pi epsilon naught R cube. So we take the vector R cap. So VC is equal to P dot R cap upon 4 pi epsilon naught R square, where R cap is a unit vector. So it is defined as R vector upon R. On the axis, theta is equal to 0. That is towards plus Q. And theta is equal to 180 degrees towards minus Q. And you know cos 0 is 1, cos of 180 is minus 1. So V axial is equal to plus minus P upon 4 pi epsilon naught R square. This is the maximum value of potential. Okay. So at equatorial point, theta is equal to 90 degrees, cos theta is 0. Therefore, V equator is equal to 0. This is the minimum value of potential. Now, let us consider the electrostatic potential due to a system of charges. So, we have a system of charges Q1, Q2 up to Qn. Potential at P due to Q1 is V1 is equal to Q1 upon 4 pi epsilon R1. Similarly, potential at P due to charge Q2 is V2 is equal to Q2 upon 4 pi epsilon R2. Similarly, potential at P due to the charge Qn is Vn is equal to Q1 upon 4 pi epsilon Rn. By superposition principle, V is equal to V1 plus V2 up to Vn. Therefore, V is equal to Q1 upon 4 pi epsilon R1 plus Q upon 4 pi epsilon R2 plus so on up to Qn upon 4 pi epsilon Rn. So, we can write V is equal to summation Qn upon 4 pi epsilon naught Rn. N goes from 1 to N. For continuous charge distribution, integration is used instead of summation. So, that's it. Thank you. To be continued.